Have you ever stopped to think about how many bearings exist around you right at this very moment? It's present in your skateboard, in your bicycle, in the wheels of your car, on the treadmill at the gym, in airplanes, trains, ships, in the industrial engines that drive our society. These small steel components are true invisible heroes of modern engineering. But do you know how they're manufactured with such precision? Today we're going to dive into the behind the scenes of an industrial bearing factory and reveal every stage of this fascinating process. Get ready, because what you're about to discover might completely change the way you see these small marvels of engineering. Stay until the end, because we have an incredible surprise for you. Here at Factory Manufacturing, we unveil the secrets behind the fabrication of products you use every day. From microscopic components to gigantic machines, we show how engineering and technology unite to create the incredible things that move our world. If you're passionate about industrial processes, manufacturing, and technological innovation, you're in the right place. Subscribe to the channel and hit the bell icon so you don't miss any video from our journey through the fascinating world of industrial manufacturing. Before we enter the factory, you need to understand what makes bearings so essential. A bearing is a mechanical component that reduces friction between parts in rotary or linear motion. Imagine trying to spin a heavy wheel directly on a metal shaft. It would be extremely difficult and cause rapid wear. Bearings solve this problem by placing rolling elements, such as balls or cylinders, between moving surfaces. There are bearings in practically everything that rotates or moves: giant wind turbines that generate clean energy, airplane engines that cross continents, industrial machines that produce everything from food to automobiles, medical equipment that saves lives, and even in your skateboard or roller skates. The global bearing industry moves billions of dollars annually. But here's the fascinating detail. A high-quality bearing can withstand enormous loads, spin at incredible speeds, and last for decades, all with manufacturing tolerances measured in thousandths of a millimeter. How is this possible? The answer lies in the extreme precision of the manufacturing process you're about to discover. And believe me, each stage is more impressive than the last. It all starts with the right raw material. High-performance bearings are manufactured with special high-strength steels, usually chrome steel known as AIC 52100 or stainless steels for corrosive environments. These steels contain carefully balanced alloying elements: chromium for hardness and corrosion resistance, carbon for mechanical strength, and manganese to improve hardenability. Steel bars arrive at the factory in standardized dimensions and undergo rigorous quality tests. Spectrometers analyze the chemical composition with impressive precision, ensuring that each element is in the exact proportion. Any minimal deviation can compromise the final product. After approval, the bars move to the cutting sector where high-speed automatic saws transform them into blanks, rough pieces that will become the future bearing rings. Here we already begin to notice the industrial scale. A single saw can process hundreds of pieces per hour. But you must be wondering, how do these rough and irregular pieces transform into perfectly circular and polished components? The magic is about to begin. The machining process that comes next is where true precision comes into play, and I guarantee it will surprise you. Now we enter the heart of manufacturing. The steel blanks proceed to state-of-the-art CNC lathes, computer-controlled machines with astonishing precision. Here, something mesmerizing happens. Carbide tools spin at very high speeds, while pieces are molded into perfectly circular rings. The turning process removes excess material and creates the approximate dimensions of the outer ring and inner ring of the bearing. The cutting tools, made of tungsten carbide or ceramic, work at speeds that can exceed 3,000 revolutions per minute. The heat generated is so intense that cooling systems constantly spray special fluids onto the piece. The CNC lathes follow millimetrically calculated programs. Sensors monitor every movement and make real-time adjustments. The precision is such that tolerances reach only a few microns. That's smaller than the thickness of a human hair. Impressive, isn't it? But here's a fact that will surprise you. Even after all this precise machining, the rings still aren't ready. They need to go through more finishing stages, and each one is crucial. The raceways where the balls will roll need to be extremely smooth and perfectly round. But the process is just starting to get really interesting. While the rings are being machined, another sector of the factory works on producing the rolling elements, the balls or rollers that will sit between the rings. This process is absolutely fascinating. For balls, the process begins with special steel wire that's cut into small pieces. These pieces go through forming machines where they're squeezed between dies under extreme pressure, transforming into almost perfect spheres. Yes, you heard that right. Metal being molded as if it were putty. Next, thousands of these balls go to lapping machines where they roll between rotating discs while an abrasive compound gradually polishes them. This process can take hours, but the result is extraordinary. Perfectly round balls with a mirror finish. For cylindrical or tapered rollers, the process is different. Steel bars are cut and then ground in specialized machines that ensure each roller has the exact diameter and perfect surface. Quality inspection here is relentless. Computer vision machines check each ball or roller, identifying any microscopic imperfection. Defective parts are automatically discarded. Nothing less than perfection is accepted. We've arrived at one of the most critical and spectacular stages: heat treatment. This is where steel gains its extraordinary mechanical properties. Get ready, because this part is literally hot. The rings and rolling elements enter gigantic furnaces where they're heated to temperatures exceeding 800 degrees Celsius. The inside of the furnace looks like the heart of a volcano, with parts glowing in incandescent red. The atmosphere inside the furnace is precisely controlled to prevent oxidation. After reaching the exact temperature and remaining there for the programmed time, quenching happens. The parts are rapidly plunged into oil or special polymers. The thermal shock transforms the crystalline structure of the steel, making it extremely hard, capable of supporting immense loads without deforming. But steel that's too hard is also brittle. That's why the parts return to the furnace for tempering, a moderate heating that adjusts the final hardness and adds toughness to the material. It's a delicate balance between hardness and strength. The result? Components that combine diamond-like hardness with the resistance needed to function under extreme conditions for years on end. After heat treatment, the parts are slightly deformed and have an irregular surface. It's time for the final finish, the most precise stage of all. And this is where technology really shines. The rings enter high-precision grinding machines equipped with diamond wheels that spin at extremely high speeds. These wheels remove microscopic layers of material, creating the raceways where the balls will roll with absurd precision. We're talking about tolerances in the order of half a micron. That's 500 nanometers. But it doesn't stop there. Then comes superfinishing, a process where special abrasive stones polish the surfaces to a spectacular level of smoothness. The raceways become so smooth they reflect light like mirrors. This perfect surface is essential to minimize friction and maximize bearing life. Throughout the process, computerized measuring instruments constantly check dimensions. Any part outside specifications is automatically rejected. The demand is so high that some factories work in climate-controlled rooms because even minimal temperature variations can affect measurements. And you'll be surprised by this. The machines are so sensitive that even the vibration of a truck passing on the street could compromise precision. That's why many factories use special foundations isolated from the ground. Finally, we arrive at assembly. All those components manufactured with millimetric precision now come together. And believe me, this stage is more complex than it seems. On highly automated assembly lines, robots with advanced sensors pick up the inner and outer rings and position the balls or rollers between them. The spacing needs to be perfect. To keep the balls equally distributed, a cage or separator, usually made of stamped steel or high-strength polymer, is inserted. In some bearings, rubber or metal seals are added to protect against contamination. Others receive sealed permanent lubrication. Each type of bearing has its assembly peculiarities. After assembly, each bearing undergoes rigorous testing. They're spun in special machines that measure torque, noise, and vibration. Acoustic sensors detect any abnormal sound that might indicate invisible defects. Defective bearings are identified and immediately discarded. Approved bearings receive laser markings with information about model, manufacturer, and technical specifications. These markings are permanent and fundamental for traceability. Before leaving the factory, bearings undergo one last rigorous quality control. Samples are taken to laboratories where they're subjected to destructive and non-destructive testing. Coordinate measuring machines verify each dimension with incomparable precision. Hardness tests confirm that heat treatment was perfect. Some bearings are tested to failure to validate their expected service life. These tests can last days running continuously. Approved in final inspection, bearings are carefully cleaned, receive a protective coating against corrosion, and are packaged in individual boxes with anti-static protection. Packaging isn't just for transport. It ensures the bearing reaches the customer in the same perfect conditions it left the factory. Barcodes and QR codes allow tracking each bearing from raw material to final application. If any problem arises in the future, it's possible to identify exactly when and where that bearing was manufactured. And so ends the incredible journey of manufacturing an industrial bearing. From rough steel bars to extreme precision components that support tons and spin millions of times without failing. Impressive, isn't it? Now I want to know from you, which stage surprised you most? Was it the incandescent quenching, the microscopic precision of grinding, or the complexity of automated assembly? Write in the comments. The stage that impressed me most was, and complete with your answer. I'll read all comments and respond personally. If you enjoyed this dive into the world of industrial manufacturing, leave your like, subscribe to the channel, and share with that friend who's also fascinated by engineering. And don't forget, hit the bell icon so you don't miss the next videos where we'll unveil other incredible industrial processes. This is Factory Making, and see you at the next fabrication.